recording. So dear friends, dear colleagues, welcome to our seminar. So the concerns were huge in the last years with COVID, with the pandemic. And we all have the impression that this is coming to an end. But these days we have other concerns, which are very serious, and in particular for those who live in Europe, in the eastern part of Europe. Yes, so but our seminar continues, and our speaker today is Shimrit Shtern from Technion, Haifa, from Israel. Shimrit received her PhD in 2015 from the same institution under the supervision of Professor Ben Tal. And she spent 3 years at MIT working in the group of Timas, and moved back to Israel to Technion. Shimrit is a Technion assistant professor, and she's working on different cool topics, namely on robust optimization, on data-driven optimization. She's developing first-order methods for no-smooth, non-convex optimization. She's working on STP problems. So this is a very wide research profile. So today's talk will be on first-order algorithms for convex bi-level optimization problems. Shimrit, thank you very much for accepting our invitation. So 45 minutes for a talk.
Thank you very much, Radu, for inviting me. So I hope this will be a 45-minute escapism for all of us. I'm going to present today work that I did with my master's student Lior Doron about solving a simple convex bi-level optimization problem. And feel free to ask questions during if you have any. Otherwise, I tend to talk very fast, so and slow me down if need be. So all of you probably know what bi-level optimizations problems are, but I am going to talk about a subfamily of these problems, specifically simple bi-level optimization, in which we optimize over a function omega on a set X star, where X star itself is an optimal solution set of another function phi. And we assume both these functions are convex. We also denote here the optimal value of phi as phi star and the optimal value of omega on X star as omega star. These kind of problems arise a lot in ML and signal processing problems, which are underdetermined. And from all the optimal solution, we want to find, for instance, the sparsest one. So maybe the most common example is we want to solve a least square problem. The least square problem has multiple solutions. And we want to find the one which is the sparsest, for instance, or the densest, in which case omega would be the L1 norm or the L2 norm, or the norm square respectively. So although everything here is convex, let's talk about the challenges in solving such a problem. So of course we can formulate this problem as follows. We minimize omega x subject to phi f x smaller or equal than phi star, where phi star is the optimal solution. Of course, this assumes that we can find phi star and a good approximation of phi star easily. But the set is not necessarily a simple representable set. This is very much dependent on phi. And so using general first order methods like subgradient projection is not necessarily easy. On the other hand, since this problem is generally not regular, since any feasible solution for this problem would satisfy the constraint of equality, then solutions that are based on duality or KKT conditions would also not work. So this arises from this, the difficulty of the problem arises, but one might say, okay, so let's assume that we don't have phi star exactly. We have some approximation of phi star to high accuracy. So although this problem would be regular, it will almost be irregular, and that would cause a lot of numerical issues in solving this problem. And anybody who would try to put this kind of problem into a solver would have experienced this kind of issues. So what do people do in practice to solve these kind of problems? They regularize. So they take phi, they put a regularization of omega times some parameter alpha greater or equal to 0. And for instance, for the case that we saw, where phi is the least square problem, if we take omega to be the norm square, we get Tikhonov regularization and ridge regression. If we take omega to be L1, we simply get lasso regression. So this approach is kind of one of the approaches to do this. Of course, these two models have also different reasons to be used, not only to find the sparsest tensor solution. But this regularization technique can be viewed as a Lagrangian relaxation of the following problem, in which we minimize phi subject to omega x smaller or equal to omega star. So this problem might be regular, and so there might be an optimal solution alpha for which these problems are equivalent. But given that we don't know omega star, finding this alpha is hard. And so one of the things that are done is iteratively solving our alpha and decreasing alpha at each time. But this is, first of all, computationally demanding. And second of all, we don't know when to stop, like how much we need to decrease alpha in order to ensure that we actually get the solution of the problem that we wanted. So an alternative is basically a family of first order methods that tries to solve this problem. But instead of solving the regularized problem every time to optimality, just these methods do one step of some optimization algorithm, iterative algorithm, and each step changes alpha such that it goes to 0, which should go to 0 also slow enough. And that actually ensures convergence. The methods differ from each other, but by what kind of assumptions they make, and as a consequence, what kind of iterative step they do. So at least the first method I know that does something like this is a method by Soledad from 2007, in which he assumes phi is a composite function of f and an indicator function over over a closed and convex set C, and he assumes both f and omega are smooth. Then suggests to do a projected gradient step at each step on this regularized function, and shows that if you decrease alpha slowly enough, then this is asymptotically converging to the optimal solution of the bilevel problem. This work by Amini and Yousefian from 2019 looked at the case where f is has a sum structure. It doesn't need to be necessarily differentiable, and neither does omega, but omega does need to be strongly convex. In the case that omega is strongly convex, that they actually prove a rate, and the rate is for converging to the optimal solution of phi star. So it doesn't say that the rate is not for converging for the optimal solution of the bilevel problem, but on phi x, their iterates converging to phi star. The rate of converging to the actual solution of the problem is only asymptotic. And they do incremental projected subgradient step. The third method, which is debatable if it's a first order method or not, has very little assumption, just assume everything is convex, but the big assumption is that a proximal operator can be applied on this regularized problem. This is, of course, not true in most settings. And they show asymptotic convergence. This is one avenue of algorithms that are based on the regularization. Another avenue are under similar but not the same assumptions. They assume that omega is smooth and strongly convex, and phi is a composite function where f is of course smooth and g is an extended value but convex and proper and closed and all the nice properties. And they show convergence again only to feasibility, only of phi x to phi star. And the first one, which is actually the first work that showed any rate of convergence. So this work predates the work we saw before by Amini and Yusufian, is a work by Amir Beck and Shalom Sabach. They call their algorithm MNG. MNG is based on cutting planes, and each iteration, they optimize omega over the intersection of two cutting planes. This is usually easy where omega is the L2 norm square, for instance, but it might be harder in other scenarios. And they get a rate of convergence of O of 1 over square root of k. Later work by Shalom Sabach and myself suggested a different algorithm based on sequential averaging on a gradient step on omega and a proximal gradient step on phi. And we show rate of 1 over k, again, feasibility convergence. And we also extended it to the case where omega is a sum of Lipschitz continuous and smooth functions, and we did it by smoothing. So of course, the rate there is also dependent on the smoothing parameter. And finally, this work extended our work, on our algorithm, which we call BigSam, by taking inertial steps. Although numerically they show that in some cases they get superior performance, they only prove asymptotic convergence. So what is the motivation of what I'm going to show you today? The motivation is the L1 norm. The L1 norm is a very simple function, but it's neither strongly convex nor smooth. And we want to solve the problem for these kinds of functions that we will refer to as norm-like functions, and I will give the exact definition of this norm-like later on. Our algorithm is called italics, iterative approximation level set expansion, and I'll explain later why it is called that. But the key point is that we do not require omega to be neither smooth nor strongly convex. It is easily applied to any LP norm, as we will see other norms as well. And it produces the following. It produces a rate of convergence for phi to phi star, but it also produces a rate of convergence of omega to omega star, which is, to the best of our knowledge, the first of its kind, first of such convergence proven so far using first-order methods. And this convergence is slightly slower. So it's 1 over square root of k, where the convergence of the feasibility is 1 over k. So this is just a comparison. I wanted to highlight that additionally, we do deal with the special case where g is equal to 0, meaning phi is a smooth function, and there we can get even a slightly better result that omega is super optimal, meaning that at each point of the algorithm, our value for omega is actually smaller than the optimal value. I will not, unfortunately, have time to get into this case in the talk, but I will be glad to discuss it afterwards with anybody. So the key idea of our method is if omega is simple, we can either compute projections or linear oracle on its level set. And that is the key. So we can actually look at the following problem where we minimize over x and z phi of x plus norm of x minus z squared under the constraint that z is in the alpha level set of omega. Okay, and this function, I will refer to it later on. And minimizing over this function for a specific alpha, the result is H alpha. And H alpha as a function of alpha has nice properties. First of all, it's convex. It's strictly decreasing until the point omega star. And from that point on, it remains constant with value phi star. So what we want to do is to approximate solutions to P alpha. And we will see what I mean by approximate. And find the smallest alpha for which H of alpha is epsilon close to phi star. So why do we call our approach italics? Because it basically consists of two steps. In the first steps, we approximate the optimal solution of H alpha. And approximate means we don't necessarily need to get to optimality, but we need some indication if we're too far from optimality. If we are too far from optimality, we can increase alpha, but we need to do it very carefully in a way that we don't exceed omega star. So just to illustrate, for the least square problems in 2 dimensions, so we have the line, this, let's say it's the optimal solution set. And we have the blue diamond, which is the level set of the L1 norm. And we're solving the problem over this set, but we identify that the optimal solution, which is in this point, is too far from the red line. And so we can enlarge the level set and continue to do so until we reach close enough to the line. So schematically, our algorithm is as follows. We assume we have some epsilon, which is our accuracy. We assume we have a phi bar, which is a number which is, of course, greater than phi star, but smaller or equal than phi star plus epsilon divided by 2. So let's just pause on these assumptions that we have this phi bar. So of course, the problem of optimizing phi is easier than the problem of solving the bilevel problem. And so we assume we can run an algorithm in parallel to give us such a phi bar. And this algorithm will, of course, be at least as fast as any algorithm to solve the bilevel problem. So in that regard, this is not a very conservative assumption that we have such a phi bar. We also assume that we have an alpha 0, which is a lower bound on omega star. So this could be, for instance, the minimizer of omega. And we have x0, which is in the domain of phi, and z0, which is in the level set, in the alpha 0 level set of omega. And we have an approximation oracle and an expansion oracle. The approximation oracle takes the previous point, the previous alpha, phi bar, and our epsilon, and returns a new point and a number row. This number row will serve as a lower bound on the gap between H of alpha and phi star. And how to achieve such a row, we will see. If the point we get is close enough to the value of phi bar, then we end because xk will be close enough to the solution. And otherwise, we will do an expansion and we will discuss again how to do this expansion to get alpha k. So from now on, we will discuss the details of how we construct this approximation and expansion oracle. So let's start with the expansion oracle. So the expansion oracle expects a row which is a lower bound on the difference between H and alpha and phi bar, and returns a beta, which is of course a function of rho, which is larger than alpha and smaller than omega star. And in order to construct such an oracle, we need some assumptions. So now we get to the main assumption, which is the shape of omega. So omega, we assume, is convex and satisfies two properties. First of all, its level sets are compact. And second of all, it admits a gamma global error bound, meaning for any x, the distance of X from any alpha level set of omega is bounded from above by gamma times the difference between omega X minus alpha, or the maximum between that and 0. And so the first part of this assumption is trivially holds if omega is, for instance, coercive. And the second assumption, which seems more problematic, actually can be verified quite easily by using the nice result by Lewis and Pang from '98, which basically said that we can compute gamma by taking the infimum of the norm of any subgradient of function omega at point X, which is not contained in the level set. And it turns out that all the norms you can consider, of course, satisfy these two assumptions, but also norm-like functions like the elastic net function, which is the L2 norm plus L1. So we are interested in such functions, specifically L1. So these are valid assumptions for the cases we're looking at. Under these assumptions, a valid expansion oracle would be one that takes alpha and just sums square root of rho divided by gamma. And the proof, I'm going to give a proof sketch, is 5 lines. So we take X star, which is the optimal solution of the bilevel problem. We take its projection onto the alpha level set of omega. This is, of course, suboptimal solution of P alpha, so it's an upper bound on age of alpha. So we take the fact that rho is a lower bound on age alpha minus phi bar. We upper bound this by the value of what we have inside the function which the optimal value is age alpha. And of course, since phi of X star minus phi bar is smaller or equal to 0, this is bounded from above simply by the distance squared. Now we can use the fact that omega is norm-like, plug this in, rearrange the terms, and we get exactly the expansion oracle. And it guarantees, of course, that this result is smaller or equal than omega star. So what these results give us is how many expansion oracles we need to apply during the run of the algorithm. We denote this by n. And the result says that the number of expansion oracles that we need to apply is smaller or equal than 1 over epsilon. And moreover, the distance between the value of omega at point xn and omega star will be smaller or equal than some constant, which is dependent on the starting point, and square root of epsilon. And it depends on the starting point because it's simply the Lipschitz constant of omega on a compact set that depends on the starting point. So this is our first result. So the question is, okay, we know how many expansion oracles, but this is not the main effort in the algorithm. The main effort will be to optimize over P of alpha. So in order to understand truly the computational cost of this algorithm, we have to go to the approximation oracle and see what we can do there. So in order to talk about the approximation oracle, we need to understand what it inputs and what it outputs. So we assume it inputs an alpha, which is bigger than the minimizer of omega, and a phi bar, which is bigger than phi star. And this oracle should give us either an indication that age alpha minus phi bar is too big. Too big in our case is bigger than epsilon divided by 2, in which case it just should give us a number between the epsilon divided by 2 and age alpha minus phi bar. Otherwise, it just recognizes that we're close enough to phi bar and gives us back X and Z. And if you didn't know this, there is intersection between these two conditions, but this is fine. In this case, either condition can be applied. But of course, we would rather apply the second one because that means that the algorithm is done. So in order to construct such an operator, again, we need to assume something. So let's assume that our function phi is a composite function with the standard assumptions. F is LF smooth and G is proper closed and convex. And under these assumptions, we can also build the function phi hat alpha y, which, if you recall, is exactly what we had in the minimization, which gave us h of alpha. So this function is also a composite function. And it's a composite function with very nice properties. Specifically, we can say that phi hat of alpha is a sum of f hat and g hat of alpha, where f hat is this nice smooth function with LF plus 2 Lipschitz continuous gradient. And g hat of alpha, our non-smooth function, is actually decomposable to a function g, which is applied on y1, and the indicator function, which is applied to y2. And this separability will serve us when we're trying to find an algorithm to solve this problem. So our main idea came from looking at general conditional gradients. So this is the first method on which the approximation oracle would be based on. So just to remind those of you who forgot, the generalized conditional gradient assume that we can at each point optimize over a generalized linear oracle. The general linear oracle would just give us the minimum, where here we have the gradient of fy times inner product with p plus gp. This will give us a function p of y, and this gives us a direction p of y minus y. And we take the current point and we go in this direction, and we need to choose a step size in going this direction that gives us the convergence that we want at end. And there are various choices for step size, and we will talk about one of them. But the entire analysis of this algorithm is based on the quantity called S. This, I think, is the standard notation, and which is just this function, which is actually an upper bound on the optimality gap. So it bounds from above the distance between phi of y and phi star. And we also, because we usually assume the domain of G here is bounded, this S also gives us a sufficient decrease measure of how much we decrease the function in each iteration. So the combination of these two elements is what enables us to get the 1 over k non-convergence of conditional gradient. So we can, of course, apply this algorithm to phi at alpha with these changes, okay? And under the assumption, of course, that the domain of G is compact. So first of all, let's look at our function P. So the function P can actually be divided into two. One will be the generalized linear oracle on G, and the other will be a linear oracle on the level set, the alpha level set of omega. So assuming that we have a linear oracle on G, generalized linear oracle on G, and we can compute such a linear oracle on the level set of omega, this will be a very easy thing to compute. And this separability is because our function g hat alpha was separable. And the alpha here will be the diameter of domain G and the level set of omega. This is supposed to be the alpha level set of omega, which is of course bounded by the omega star level set of omega. So this everything here is bounded. And so we get the 1 over k rate of convergence for phi hat alpha, but this is not what we're actually interested in. What we want is rate of convergence for the entire algorithm after we change the alphas. So it turns out that the fact that this S of alpha is an upper bound on the distance from age of alpha allows us to stop each iteration of the approximation algorithm early enough and obtain the same rate of convergence over the entire sequence. So our approximation algorithm will do the following. So I think the key here is this thing. Okay, this will be our what we call rho before. So we notice that if this condition holds, then rho, which is exactly this value, is a lower bound on age alpha minus phi star. So if this holds, then rho is indeed a lower bound on the optimality and greater than epsilon divided by 2, which is what we required to begin with. And as a result, we can stop it early enough. And of course, if this is not true, then we got a close to optimal solution. And the consequence of all of this is that the number of CGZ approximation that we need to, the amount of GCG iterations that we need throughout the run of Vitalik's algorithm for a given epsilon is of order 1 over epsilon, because it's K, which is the order of 1 over epsilon, plus N, which is the number of outer iterations, which is also order of 1 over epsilon. So for the above Oracle implementation, we get this iteration complexity. And what I showed you, we assume that LF was known, but actually it doesn't need to be known. There is a nice paper from 2020 that shows that LF can be approximated locally and still get the rate of convergence. So this is nice because we don't like kind of global constants in our algorithms. And our methodology is actually more general, and we can use other Oracle implementations. For instance, one of the very kind of straightforward thing to do is use proximal gradient. However, proximal gradient has two issues, one advantage and one disadvantage. The disadvantage is that we can't use S of alpha because that is not something that is computed during the run of the algorithm. It's something that is computed during the run of the GCG. So we can't use this, this optimality measure. We need another optimality measure. On the other hand, because the proximal gradient is a decreasing, generates a decreasing sequence, and it does not need the domain to be compact, we can actually not restrict ourselves to function where domain G is indeed compact. So I think we have time, right? So let me just go over what we do for proximal gradient. So this is just a proximal gradient operator for a general phi. And we look actually at S tilde of Y. S tilde of Y assumes that the level set of phi of Y is smaller or equal than some D of Y. Okay, this is an assumption. Under this assumption, if we define S of tilde like this, we get that this is an upper bound, what we call here S dy of Y. What is S dy of Y? So imagine that we perform generalized conditional gradient, but on top of having phi, we also restrict ourselves to the level set of our current point. So we're only optimizing over this level set. So this may be hard, but the point is that the solution will give us this optimality measure S, which will be an upper bound on the optimality gap. And this is exactly what we get. So on one hand, we get that S tilde is indeed an upper bound on the optimality gap. On the other hand, we get that S of tilde is a sufficient decrease measure, and this is just from the proximal gradient. This is just from the definition. We just move things around and we get this. This even, I think, is an equality here. So we basically get the same two properties that we got for conditional gradient and for S. So of course we can convert everything now, phi eta of alpha. And now the assumptions I had here about the level set being bound is no longer an assumption. Actually, we can show, because of the structure of phi eta of alpha and because of the decreasing property of the proximal gradient, that first of all, this is indeed bounded, and we can give a bound. And so we can use this bound onward. And similarly to what we saw in the conditional gradient, we can separate the proximal gradient operator into two, one on G and one on the omega, the alpha level set of omega. And again, assuming that this projection is easy, then we can apply this algorithm very easily. So actually what we have, the first property in the lemma, this is what enables the early stopping. This is what enabled the early stopping, the conditional gradient as well. And the second is what enables the 1 over epsilon convergence rate. The same is in the conditional gradient. And I'll just remark that this is not specifically for proximal gradient. There is a family of algorithms called PDA algorithms that connect to conditional gradient. There's a nice work by Amir Beck, Shom Zabach, and Edward Paus about this. And actually any algorithm that falls into that family can be used. So we got this flexibility, and we can use either proximal gradient, conditional gradient, or even a mixture of the two. And so we get this rate of convergence that we discussed before. So I would conclude with two numerical experiments. So in one of them, we took a sparse signal. We put a linear transformation on it and added some noise. And this is our measurement B. And we want to solve the least square problem under an elastic net omega. And we did 100 simulations of the noise. So what you see here is average over 100 simulations. So the top, so we see 3 data sets, and this data set is just how we generate A. The top row graphs look at the optimality gap for phi, and the lower graphs for the optimality gap for omega. So what we compared here is what we could compare. So first of all, this is a subgradient-based approach. It's not the incremental subgradient because here we have only one function, so it's a subgradient-based approach. And as you can see, it's very, very slow, so it doesn't reach anywhere close to phi star. Next, we look at Big Sam with 2 smoothing parameters. One is big, 1, and the other is small, 10 to the power minus 3. So when we see that when we take it to be too big, we actually converge to something which is not optimal in some cases. Because what we did, we approximated omega with a function which is, its optimal solution is very far from omega. If we take the parameter to be too small, then we get to the optimal solution, but I don't know if you can see it here, especially in the BART data set, the convergence rate is very small because we pay for this small data. And then we have the italics with the PG approximation oracle and the italics with the GCG approximation oracle. And here we see that actually the conditional gradient-based approximation oracle does better, both in terms of omega and in terms of phi. Next, we wanted to look at the L1 norm, which is kind of our original motivation. The problem is we didn't have anything to compare to because there is no algorithm that can deal with this and have provable convergence. So what we found is first that the proximal gradient in this case was faster than the conditional gradient. But we wanted to compare to something. We wanted to show that we actually converge to that there are no numerical issues, converge to what we need to converge to. And in order to do that, we basically did iterative regularization. So we solved the problem multiple times with decreasing regularizations, which are here. And we plotted it in the red lines for each of the data sets. So this is multiple, so each point here is one run of a regularized problem. The black and blue lines are the italics with the PG approximation oracle and the italics with the CG approximation oracle, but this is one run of the entire thing. So what we can see is we follow the red line. So we basically get the same thing we would have gotten if we did iterative regularizations, but we can do it in one shot. And just to conclude, so as I said, italics give us 1/k feasibility and 1/√k optimality rate for norm like omegas. But it gives us more than that. I showed you the algorithm for an epsilon, which is given to me in advance, but this does not necessarily need to be the case. We have a version of the algorithm which basically changes epsilon or decreases epsilon with time, and that's actually the results I show you is for this algorithm that decreases epsilon. As I said, we get super optimal solutions where G is equal to 0. We can get accelerated rates under additional conditions on phi and omega. And we can allow for the outer functions to be of the form omega of some linear function, where omega is still a norm-like function and gets similar rates. And with that, I will conclude slightly ahead of time, I think.
Thank you very much, Shimrit, for a very interesting talk. Are there questions?
I think Emmanuel has a question.
I was just applauding, sorry.
Thank you, sorry.
I found it very interesting and look forward to see the slides in detail because my screen is so small that I cannot actually for the numerical
no problem.
figure out the details. So just for a quick understanding, if I may, Radu?
Sure. Yeah.
Okay,
sure.
sorry. The horizontal axis, you had so the very vertical axis is always delta phi, but actually it's the same as phi, right? Because the optimal value is 0 or not?
Yes, but we don't know the optimal solution is not necessarily 0.
System, so you have always 0 is phi star. So delta phi is phi. Is it correct?
Not necessarily. There might not be a solution in which you get 0.
Okay, so you're always also considered overdetermined systems. That's what you say. No solution.
Well, there might be no solution, yes, but there might still be more rows in A than there is no solution to AX equal to B.
Yes,
but there is still a solution to the
additive
minimization
noise
of the least square problem.
You leave basically, so that's not full rank, and therefore you leave the domain of solvability in some.
Yes.
Okay,
yes.
then delta phi is clear to me. Thank you. And the horizontal axis in this particular case for the L1 norm shows what?
So this is a bit of a problem. We thought we don't know omega star, but we want to measure some distance from omega star. That's why we take a very small regularization and hope for that regularization, this is actually the value of omega star. And then we look at the distance from that omega star. So this 1 minus delta of omega is actually the distance from omega star, or the relative distance from omega star. So here the L1 norm, it really depends on the problem. And that's why we have it, normalized in some sense in order to compare the methods.
So you don't fix the sparsity in your simulation?
The true sparsity, the true X is sparse, but the optimal solution set for the...
It's a drawback of any convex regularizer.
Yes,
that you don't maintain sparsity.
Not necessarily. Not necessarily, although we did have some results about how sparse the solution is, but this is more about the model. So the question is the model the right model to model the problem? But under this model, we just show that we get, we converge to the optimal solution.
And time-wise, do we have some?
So time-wise, so as I said, proximal gradient was here faster than conditional gradient. It's generally, especially when you have additional G, it is faster. And so what you can see, like before, what I showed here, so this is approximately the same ranges of time. So it really depends on the problem. Here, actually, because there is this strong convexity, actually everything converges faster. In general, it will converge slower, and so you will see it keeps going down just very incrementally at each point in times, but it does correspond with the theoretical results. So 1 over k kind of convergence.
Okay, thank you very much.
Thank you. Other questions? So Shimrit, I have a couple of questions. So can you say some words about how expensive is to project on the level set of omega?
So projecting on depending on the problem, right? So on elastic net and level and L1, this is very simple, right? This is basically.
But what about other examples and other problems?
Again, any omega that you can do a proximal operator on, you can project on the level set, basically.
Okay.
Specifically, you can you might need to bisection additionally, but this is very fast. But it's more or less equivalent to doing a proximal up to some log n. And the linear oracle is even cheaper, usually.
But then instead of considering level sets, wouldn't it be kind of more meaningful to consider the epigraph? So just not to fix the upper bound. Since there are formulas for projections on epigraphs. There are even closed formulas.
Right. So this is so epigraph is actually harder than projecting over the level set.
I wouldn't say so. So there are for many class of functions, there are exact formulas for projection on epigraph. I mean, there are,
yes, I'm saying, but if you can project on the epigraph, you can definitely project on the level set with at least
Oh, really? Can one adapt these formulas? Okay, probably yes. Okay.
Yeah.
Yes, then I have another question. So, I mean, so the approach is as follows, just to put it in a concise form. So you fix a level of accuracy, and then you count the number of iterations you need to achieve that level. And this is 1 over epsilon. But can one say something about the convergence of the sequence of iterations?
On the sequence of iterates itself?
Yes. So the statement is in terms of function values.
Yes. So actually, the more natural statement with regard to convergence of X, let me go back. So I'll tell it as follows. So what we actually get here is we know that this function, or phi hat of alpha, is smaller or equal than epsilon. So we know 2 things. We know phi of x is smaller or equal than epsilon, and we know the distance of x from the alpha level set of omega is smaller or equal than epsilon.
Okay.
And since alpha will be smaller than omega star, we also know the distance from the omega star level set is smaller or equal than epsilon. So this is on the iterates themselves. With regard to phi, we don't have a distance, because in order to get a distance with regard to phi, you need some kind of error bound with regard to phi, or some strong convexity with regard to phi. Which we don't want, because if phi is strongly convex, for instance, then of course.
Okay. I mean, since you said at some point that there are no algorithms to compare your method with. I mean, there is a series of papers on similar problems, but then the methods proposed there are penalty type methods, even if the constraints are non-smooth. But the statement is there. I mean, there are no rates there. Right? So from this point of view, your method is better. But in these methods, one can prove a Gaudy convergence of the sequence of iterates to a solution of the bilevel problem. Probably it would make some sense just to compare.
So in that sense, we can prove the asymptotic convergence of our method to an optimal solution of the bilevel problem.
Okay.
Asymptotically, there is no problem to prove it, but you can get a rate.
Yes.
On this.
No,
but yes, this method asymptotically, you can just show what happens when epsilon decreases to 0 with time, and it will converge to the optimal solution.
Okay. Yes. So yes, I mean, so I was talking about just convergence, not necessarily rates. I mean, there is
So it does converge, definitely.
Okay. Yeah. But still, I mean, for instance, Edia Touche, who wrote like 10 years ago, like 2 or 3 papers on penalty methods. And so they would very much fit your problem formulation. There is no rate result there, but just for for comparison, just to see how these 2 methods behave. And in particular, of course, this these algorithms make sense if the constraint function is non-smooth. Otherwise, for smooth constraint functions, there are of course classical penalty methods. But there are some, even if this constraint, or how to call it, the lower level objective function is non-differential. Okay? And then one use approximate. Okay. So are there other questions? So then let us stop here. Oh, do you have?
May I ask one question, please?
Sure, of course.
Sorry to interrupt, but Shimrit, very interesting talk. I really enjoyed it. So just to give a little bit of introduction, so I'm a Nuge. I've just completed my PhD under Professor Boris Modukovic, and I just pivoted my research into this area of bilevel optimization. So I was just keen on knowing it's a very natural choice to use norm square as a regularization technique. So do you have any insights into if we use some other penalty functions, should we be getting a similar result, or they would change up to a certain extent
I would
if
assume,
the nature of the...
Yeah, I would assume that any kind of Riemannian distance would probably be good, but that would then need to depend on probably the structure of omega. We actually really relied on the fact that we have this penalty function here, and we needed it to be smooth in order to be able to do all, or to apply the methods that we wanted to apply, and that's why we wrote it like this. But yeah, so I think Riemannian probably added distance here would work. And I'm trying to think, because originally we had this a bit shifted, and we didn't have this regularizer, and then we needed to do more complicated operators, which are not necessarily nice. And this just allows us to decouple everything, but also get nice rates on top of it. So that is kind of the most intuitive thing I can think of. I'm sure there are others, but then you might be in trouble in terms of what kind of operators you can apply. Yeah,
I think with all these algorithms, we tend to relax a little bit, and then other parameters tend to get affected. So yeah.
Exactly.
Yeah. So yeah, it was just a thought, but yeah, interesting, very interesting approach. Thank you for your answer. Yep.
Thank you very much. Okay, are there other questions? So then let us stop here. Thank you, Shimrit, again for a very interesting talk and for an interesting discussion. I just want to announce that we will post the video of today's talk and the slides on our website, and the video will be also posted on our YouTube channel. And like to also to let you know that our next speaker will be Yuni Liu from Tsinghua University, Beijing. And I would like to wish you a great afternoon, a nice weekend, and yeah, more peace than the last days, the last week. And let's hope for the best. Thank you very much. See you next Monday.